Open source, open source
firmware is a very important part of the open source movement, and increasingly it will become important for the buzzword of the day, the Internet of Things, IoT. Philip will tell us about development of open source firmware and also give an outlook onto the future, what we can expect in the future. And I think it's going to be a very interesting talk. I'm glad to see you all here, and let's help him and give a warm hand to the speaker.
Yeah.
Okay.
So
we talk about open source firmware today, a love story. The slides are in English. I'm sorry. I tried to translate them into German, but it doesn't really work. So open source firmware or firmware development is mostly dependent on English terms, and to translate them really hurts, and nobody's going to understand them in German. So I'll talk about me. I'm head of 9-element cybersecurity. We made the Open Source Firmware Conference. I'm Coreboot and Linux Boot project member, and also in the leadership there. Maybe some of you know me from not the Hack Center, but from the Coreboot flashing. I'll do that on Congress for a few years. I'm active in the hackerspace. I do IT security. I've been doing it for 10 years, and for 5 years I've been firmware developer, and you can contact me via Twitter or my company email. So, but what's the motivation? Why do I do this? And I wanted to do a talk about firmware development to people who don't know anything about that, because we want to have new developers, because it's very important. And one of the things is that a lot of that is under NDA. It's very complex, and people say, oh my God, firmware, that's even more complex than the Linux kernel development. And yes, that was one of the reasons. The other was, everybody says BIOS, and BIOS is basic input-output system, and that has been dead since the year 2000. And it means we talk about more modern things. And the other story is, why is open source firmware development important? And there's this nice guy, maybe you've seen him, that's Minich, and he works with Google. And when he was at Los Alamos National Laboratories, they had a CPU cluster, about 1,024 PCs. That was a long time ago, and there wasn't a lot of special hardware and very low level and so on. They had set them up and started them and hoped that the cluster would go online with all these computers, and they found after 5 minutes that nothing was happening. And then they sent an intern to look at the display and to connect the display and see what happened, and they all said press F2 to continue. And with servers, that's not really the best solution if the firmware requires a manual input, and in the end it prevents one from starting the systems. And they really fought with that for years. The interns always had to restart the computers, and they always had to press F2, and it wasn't very nice. And that's one of the reasons, a good story, why in the end we should think about open source firmware. At first, let's talk about some hardware. It all starts with hardware, and after that we'll look at what is firmware and about what firmware are we talking. This is a board by Facebook. It's called the Open Cellular. It's really an open source base station, or it's an open hardware base station. They really do open hardware. You can download the boards, the circuit board layouts, and everything is there, and you can do that at GitHub. I took that as an example, and this thing also has open source firmware. But if you look at a block diagram these days, what's in it? There are several circuit boards that are stacked upon each other. It's not everything on one board, but there are several boards for various reasons. One is the host processor, there's the power supply, the front panel, and there's that also is part of the main board. It's a huge block diagram. There are several components, and it's all quite complex. And if one takes a look in some more detail there, we'll find that down there is TIVA, and there's Intel Atom, and there's something about a power controller, and there's a DPM, and they all have firmware. And if we have a laptop or something like that, a ThinkPad or something like that, there are 15 different processors. Some of them are microcontrollers, but some are really faster than that. There's some ARM cores or maybe even x86. And there's firmware everywhere these days. You just don't see them. You think you have one processor and there's a BIOS firmware or something. Well, no, not really. There's really a lot more. There's firmware everywhere. And what we talk about today is the host processor firmware, because if we talk about all the firmwares, that would be too much and would take days to get through. In general, you can say that hardware is made by OEMs or ODMs, original design or original equipment manufacturer. This is, for example, Lenovo, Dell, or HP. They don't make the hardware themselves. They subcontract ODMs, for example, Wistron or Quanta, to make the hardware, and they also design the layouts. And Lenovo only subcontracts these and then sells the hardware to the customer. These OEM or ODM, they're also the customers by the sub-vendors, and the system-on-a-chip vendors are, for example, Intel, AMD, Qualcomm, Cavium, and other CPU manufacturers that you know. Intel's customers are not we are not, but in reality, Lenovo and HP are that produce the hardware are Intel's customers. And what's also important is that most of these OEMs don't really like to write the firmware themselves, but this hardware requires firmware, so they go to independent BIOS vendors. It's not a nice label. They should be called independent firmware vendors, but they're companies that make the firmware on contract from the manufacturer, and they boot up the hardware and make everything run. And in the end, that's really the logic behind it. So what we look at today is the host processor firmware. That's a flash chip. There's a red dot on it to identify it. Not always, but sometimes is a CP engine APU2. There's a header, and you can read out the flash. And these flash chips are everywhere in most systems, on routers, on desktops, laptops, and servers. Everywhere are these flash chips. Sometimes they have a different form. This is specific. And there's also VSON or something other packaging. And well, okay, that's what we talk about today. If we look at this flash memory, there's NOR flash, what I talked about, that I showed you, and it's connected to the SPI bus, is very fast, is very expensive because you have to put it onto the circuit board. In addition, it's quite easy to integrate. The bus protocol isn't very complicated, and there are drivers for everything, and it's quite easy. Then there's also eMMC, and sometimes it is used for firmware. It has some problems, though. For example, it's quite slow, and although it's quite cheap, it's really complicated to initialize it. But that means the firmware has a lot of work to get everything run and to get started. Some notebooks have that, but usually it's NOR flash. And then there are those microcontrollers. They usually have internal flash memory with just a small memory, just a few kilobytes, but not really megabytes or gigabytes. And so you can see here there's an external flash programmer which you need to read it, and the operating system doesn't support that, or you want to write it, and this board with the clamp there that you can also buy. And the size of the NOR flash has increased in recent years. In times of where around 2000, there wasn't a lot. There was maybe 512 kilobytes or maybe 1 megabyte. Today, in current laptops, there's 16 megabytes of memory. And Google, last week, they had a core boot tree, and they went up to 32 megabytes. That's the first one with 32 megabytes NOR flash, and it's going to be more, and some already have 512 megabytes. And with 512 megabytes, there's a lot you can do. You have, in addition to the firmware, there you can have a Linux firmware and an X server and Node.js, and whatever you want. Okay? And that means the firmware running on our systems is growing without end. There's more and more memory, and we'll have more and more firmware. And it's really uncool if it were all closed source. So let's talk about IBVs.
Und früher habt ihr, before you saw it on the BIOS screen, there's also Phoenix technology inside and many more. Many more of them are actually selling the software as well as a product, and they're producing closed source. But some of them are also producing closed source firmware for a few projects like U-Boot, Coreboot, TianoCore. So some of them are delivered as with royalty fees, and some are just giving us SDK cores. And they're getting this as a...
So the SDK is maybe about 20,000 euros or even more expensive. And in addition to that, there'll be royalty fees, which means that it's something like usage fees. So if you go there and want to sell hardware, then for every hardware you have to pay maybe 50 euros a usage fee and 50 euros per device. And if you sell a few 10,000 or 100,000, that's a lot of money. And maybe so open source firmware is a lot cooler maybe. So here's an IBV example. They have a service page for converting services. There are some that are, those are mostly the good guys, but they're not really great, but it's better than the old conservative development. And so let's see how firmware actually works. There's a flash chip, we have a host processor firmware, and how does that work? Most just press the power switch, and at one time Linux is booted or the bootloader and then Linux. And so that you can understand how that works, you can't just easily categorize it. Firmware is different, even open source firmware is different. Not everything is implemented the same way, but there are always a few things that are the same. So at first, there's an initial code, a reset vector is executed. So there's some initial code in the firmware, which is executed by the so-called reset vector. And then SRAM and cache RAM is being initialized or used. Then the system main memory is set up. Then many drivers are loaded. You can see it in Linux drivers. It loads a lot of drivers during initialization. And then some mechanisms are executed, which are used for the operating system, are needed by the operating system, which has some requirements. And then the bootloader inside the firmware is being loaded, if there is one. And then the bootloader in the operating system is being loaded, and then the operating system itself. And we look at that in some more detail, but that's roughly what it does. So let's look at the flash chip first. The flash chip can have partition tables. Some manufacturers thought it would be a nice idea if they already tell people, or the IBVs, how to partition it. And there are some reasons why, for example, Intel, there's this Intel firmware descriptor, why they do it. The partitioning is usually in 4 partitions for Intel systems, and the flash chip is used as a configuration source for the IFD, and or for the. It's a big theme there. There's the partition table header. It's and then there's one that's called GBE partition. That's the data used is required for the gigabit Ethernet. So the LAN adapter, and their configuration data for the MAC address that's there. Then there's the ME, that's the Southbridge firmware, for example. And after that, there's the BIOS, the actual firmware that does the initialization of the platform. And it's not always the case, and it's really just with Intel systems, with ARM or AMD systems or other architectures that it's usually not done. The firmware does that by itself. Then there's ROMCC. It's a strange name. It's a compiler. Whenever it is CC, that's usually compiler. And this compiler, what it does is legacy. In the end, it compiles an initial code from the firmware, and it was only done with x86 legacy platforms and Intel x86 platforms. And it was created by Erik Biedermann, and it's one huge C file with 21,000 lines of code. It's a real monster. I looked at some of the ASCII art there, and whenever there's ASCII art, it's never a good sign if there's ASCII art inside code. And what the thing does is you have to know that with old Intel systems, there's no main memory in the beginning. There's nothing, absolutely nothing. So if you don't have cache or memory, so how do you do memory management? And what you do is you use registers. So we have CPU registers. They are from the beginning, and the compiler uses CPU registers and uses that as memory. But there's some problems with that. So if you nest functions too deeply, then the registers are full and there's a stack overflow. And in this case, not a stack overflow, but a register overflow. And this is really, in the end, what happens. It's an invention of core boot, and the code is still there. And some old systems still use that. You can't do that in any different way. And with modern systems, there's SRAM or cache-less RAM. That's the platform itself. The system on a chip already supplies or provides memory. So you have some sort of memory. It's not really main memory, but it's some kind of memory. It's just a few megabytes. Cache-less RAM can everybody can imagine that. It's CPU caches. That's maybe 1 or 2 megabytes. You can use that as main memory. It's great. Yeah, it's easy to initialize, and then you have at least a few megabytes of memory in the beginning. So you can use a normal compiler. If you have a stack and a heap, you can use the GCC or CLang or something like that. But cache-less RAM is very specific for x86 platforms. If you look at this picture, you have a system on a chip and the CPU, the processor, and there's the IBB, the initial code. It's in the flash, and it has to be put into the SRAM somehow. It's copied there into the SRAM, and then later it is also copied into the main memory initially, and that's how all this booting mechanism works.
So at the very beginning, a reset is happening. The initial code block is going to be copied into some form of memory somewhere, and it has to be at a very specific position. And this is very specific to the platform you're on. So there is a platform-specific address where the CPU is jumping in upon a reset. And no matter what it is, the CPU is going to execute it. And the CPU is just jumping to this address and is just going to jump to it. For x86 this address, and then the code is executed there. This is just how the initialization of the platform is working. It's actually quite easy. So the memory is somewhere available, the memory is mapped, and the MMU is just pointing the IP to where it has to go. So this initial code that I talked about, so I distributed it a little bit. This distribution is a little bit following the core boot. So there is initial code set that is executed by the initial code vector. It is initially programmed in assembly, but today in C. But the additional thing that you do is to do cache as RAM, or you're using directly the SRAM that is available. But it's also doing, we also have an SPI flash, so where the boot data is. It is using an SPI driver and a file system driver in the SPI to load more code. So this initial code is going to be reloaded afterwards after some initial code is executed. So in the upon the reset, this is automatically executed, that several code blocks are getting executed afterwards. But the debugging is difficult. So as a cobot, this initial code is also
So this initial code uses the cache's RAM or SRAM, and then next stage is the ROM stage. So we have cache's RAM or SRAM, that's just 2 or 3 megabytes. It's not a lot. So, but we want to have more memory. We want to have the real memory. So we have to train the RAM. So maybe I could put in 10 slides about RAM training, but basically if the main memory doesn't work initially, it has timings, and if the not all the lines are the same length, then you have to do some software for training it, so for timings, and there are some static values from the manufacturer, or you calculate this in the firmware. So you have fixed RAM that's soldered on, and you have RAM that you can remove memory, and maybe there's additional information in the memory modules. And these training data that we calculate, they are usually cached. So in the firmware, in the flash, you store them, because this training for example, Intel Apollo platform, that's an embedded system, it takes 10 seconds to train the main memory. And if you do that with every start, and then the firmware has to boot more, and the initial boot takes 20 seconds, and nobody wants that. So this data is being cached, and with the next start, they are reused. And another important thing is, for example, this is the page table setup. If you have more memory than 4 gigabytes, then you need page tables. You can look at the Linux code for that. The memory management unit has to be activated, but it doesn't activate all of it. Not all firmware initializes that, and 32-bit systems, you can't really use that, and in the firmwares there's always only less than 4 gigabytes. But what's also important is that you need CPU caching, and that's really an important part. If the CPU caches have been used as main memory, but now they have to be used to communicate with the main memory, so CPU caches communicate with main memory to get it faster, and otherwise the CPU would have to access the main memory directly. That's quite slow. It's not very high performance, and that has to be activated. And another thing is, many of these firmwares have their own memory management. For example, with Godoras, or there are some features in programming languages, and there's also an allocator pool, and they allocate memory and release it again. And in this ROM stage, everything like that is initialized. And after that, we have main memory. Finally. And that means now we can do all the other funny things that we need to do. And in this stage, it's usually the case that we have the PCI device tree enumeration. So if you have PCI devices, so everybody has been using PCI. If you have lots of devices, then you have a bus. With x86, it's a standard feature, and you have to travel along the bus. It looks like a tree, and there are devices, and you can turn them on and off. And in the BIOS, you can also turn them on and off. And specific devices, you can activate them or deactivate them, and that is being done there. So the native graphics will be initialized, and if you want to see something that what your firmware does, the init graphics and option ROMs of LAN adapters or Wi-Fi or whatever, they have option ROMs, they have to be loaded, then their multi-processor initialization has to be done. There are things that are being done in this stage. You can do it earlier, but it's not always the case. There's an E820 table, and then there will be device drivers. There are a huge number of device drivers, all the things that Linux initializes as devices. That's quite important. And then there are firmware interfaces. And in general, you have to say that the last part of the firmware is the bootloader, and the bootloader is really it's an own implementation and uses the device drivers that are there, and uses and tries to load another bootloader or the operating system itself. So the firmware already has a bootloader, and before that is a bootloader, and the operating system is one. So it's duplicate code, but well, that's really the case there. So bootloader already uses main memory because we already have that, right? So overall, the firmware has 3 parts: pre-RAM, driver layer. And so pre-RAM is IBB on ROM, driver layer is the RAM stage, and that's huge. Drivers device drivers are huge in firmware, and the bootloader, the pre-RAM is usually small because there's little memory available. And let's talk about open source firmware. So there are really three people who have invented or founded open source firmware. That's Stefan Reinauer, Wolfgang Denk, and Roland Millich. Roland Millich and Stefan Reinauer have worked on Linux bytes, and it's called Coreboot these days. It has started in 1999, so we have 20th anniversary next year. It was mostly x86 architecture, and today we support a few more. And U-boot used to be called PPC boot and was supporting PowerPC. That was Wolfgang Denk, and renamed it to U-boot for Universal Bootloader, and started the same time as Coreboot as 1999. And now there are these two projects, and those were the beginnings of the open source firmware development. And if you look at this timeline, in the beginning there was the first BIOS. That was 1981. That was a long time ago. Then there were lots of closed source firmwares. I didn't list all of them. There are too many of those. And around 1998, Apple received Intel from EFI. That's not the UEFI that you have today, but there was a pre-version as a fork, so they could make their EFI stuff. In 1999, there was Coreboot and U-boot. There was the open source firmware community, and they have been annoyed by closed source firmware. In 2006, by Intel made UEFI open source later, and some part of the implementations have been open source by Intel in 2008. And after that, there was 2014 Hostboot by IBM for PowerPCs, and we'll look at that later. And today, 2018, there was Linux boot. And if you look at that, there are more and more open source firmwares. There are more than I have listed here, but why do we want open source firmware? There are a few reasons. One is that there are many small companies, such as in the Open Hardware Association, Open Source Hardware Association, they work on open hardware, and of course they need open source firmware. It wouldn't make a lot of sense otherwise. And also many closed source companies, a lot of the closed source firmware is programmed badly, and managers do reviews and they shove parts back and forth as zip files, and that's really a bad standard concerning software development. There are no quality assurance and no tests and everything. For example, if big companies want to have flexible solutions, especially if you have a fragmented firmware landscape. For example, if Facebook has 1 million servers, they are already all by different manufacturers. They all have different firmware. They all have different update mechanisms. They all have different bugs, and nobody wants that. So different interfaces, how the boot is progressing, and software debugging is hell, really, to debug firmware. It's not really easy. And also you can share features between companies. And if I implement something in our company, then, for example, Google can use that. There's open continuous integration. There's open quality assurance, open code reviews. It's not perfect, but it helps a lot. And there's also, you can employ lots of open source developers in your company, which is a good thing. And in the end, by the free software licenses, such as GPL, companies can really be pushed to releasing the source to their firmware. And so let's talk about security. Security is a huge problem because most of the security features should be auditable. You should be able to look at that. There should be documentation. Usually there isn't any for security features. The reverse engineering of the firmware isn't really what you want to do. And there is, with the measured boot functionality, if you look at, you create some hashes, but you don't really know what you are hashing. There's a kernel output, what kinds of hashes there are, and it doesn't really tell me anything about the firmware. You can get some information about that, but it's very hard to see what has been measured there, especially if there are lots of blobs. Fixing security issues is very hard with closed source firmware, and it's never done. It's not always done right. Trammell Hudson talks about really some issues there, but you should really look at that. And we have really been fighting against blobs. I didn't really want to say the word, but these are binary large objects. You've all heard about it. It's code including intellectual property, which includes some knowledge by the company, which they think they need to protect. It's just being compiled and it's an executable. And from the open source firmware, this has to be executed, for example. There's an API for that. And the whole thing is really only for modern platforms, except RISC-V and OpenPower. There's no open source firmware that doesn't have blobs. So all the manufacturers have this IP code and put it in, and that's a huge problem. Most of the manufacturers don't really know why they do it. It's just they've always been doing it like that. And in this picture, you can see there's FSPM and FSPS in core boot. Those are blobs. At different points in time, they have to be loaded by the firmware, and there's more than that. And all these blobs are loaded in the pre-RAM environment, and most of these will be loaded in the pre-RAM. The IP code is usually under NDA. It's from different companies, and they don't even make it themselves. They have secret bits that inside that, and they don't need to disclose those. And sometimes you can break the hardware if you do something wrong. And every documentation by Intel is by default it is confidential. There's no real open documentation. There's some of it, but if Intel makes hardware documentation, that's always protected under an NDA. There's some advantages to that, but they have a very restrictive management, and they have legal departments. They are not really at the height of the time. It's not really evil, but that's just how it is. And we have been fighting like that for about 20 years or something like that.
For 20 years, we have been fighting against this lockdown of the firmware, but there are many problems coming with the blobs if you're using them. That's code duplication. You have the fragmentation implementation core boot, and then in the blob, you cannot fix it. There is no debugging. Everything is not available. Documentation is under NDA. The blob interfaces are, for instance, in the core boot block, you call it, and the blob is sometimes done, and then you can continue, but you have no idea what's happening in there. But with a free software license, there's a problem in using these ones. So then you have to send this to the legal department whether you can use this. And so it's not so very nice to use these blobs. And the support of the vendors for these blobs is very often not existing. So you ask them and you might get an answer within 3 months. So many of the blobs have to be rewrapped, and so code wrappers have to be implemented. And this is not actually what you want to do with open source firmware. So if you have a look what is going to be required for blobs on the Intel architecture, you see on the right. So there is a diagram of what's needed. You have microcode update, FSPM, memory unit, FSPF, that's the part of the RAM stage part. So the Intel management engine, audio block. So you are loading basically a plethora of different blobs, and this is not actually what you want to do. This makes everything very difficult. So let's come to the more interesting and good things. So there are many open source projects in, for example, Coreboot. I mentioned them several times because I'm working there. So it is for a lot of different architectures, whatever. So there is not a good documentation, but we are a very big community. And you have in the REC channel very often about 300 people, 200 developers. So we have a public continuous integration, we have code reviews, and soon some real quality assurance. So once code is generated, it will be pushed to the hardware and tested. Coreboot is actually not a bootloader, but it can actually load a bootloader. It can actually load other bootloaders. So actually, it is there to deploy a secondary bootloader. U-boot is another community project. It's quite similar. It is supporting the similar architectures as Coreboot. The documentation is a little bit better. It has also a very big community. It also has a public CI and review. They have their own bootloader implementation. And they can also support FE runtime, so the enhanced firmware interface reload implementation. So this can be actually used to mirror the UEFI implementation. So it can actually mirror the complete implementation for Windows to access the BIOS. Core is yet another one that is helping there. ARM is there very active now. So they went there and said, yes, we want to do this for ARM64, but we are a very small community, but we are very conservative. We have no QA, no public CI, but for some month, there is Stefano Citola, and he is doing the community management. So they are going to improving, and they are improving. So they have. So also Microsoft bought into this, and they are going to use this. They're calling it Project Mu.
Then there's also Hostboot by IBM. That's for open power systems. It's the really most open architecture that you can find from the firmware point of view. There are no blobs or almost no blobs, and it's really only PowerPC. It's really only supporting PowerPC, and it's exactly for their hardware. But they also have a payload mechanism such as like coreboot, and they have a good documentation, and IBM makes lots of documentation. You know about that. They've been known for that, and there's no public CI or QA, and you can look at it at GitHub, Open Power. And then there's ARM Trusted Firmware and Slim Bootloader, OpenBMC, UBMC, Sound Open Firmware Project. There are so many others, so many other firmwares. You can take a look at all those. I listed some of those, and if you really look for it, you'll find more and more people are getting involved. About security frameworks, there's something. Everything is reused, reprogrammed, newly programmed for firmware, but there's no reuse of existing things. And there's UEFI, Secure Boot. Most of that is from Microsoft Windows. There's a good documentation. It has measured boot support, but it's really only by UEFI. There's no library that you can use independently, but it has an end-user model. So end users can really load their own keys into the firmware, and it all depends on flash protection mechanisms of the security, and you can tell it to protect parts of the flash, and there's X509 certificates. And there's another security framework. It's called Google Verified Boot. It is used by Coreboot, U-Boot, and OpenBMC, but some of it is not complete. It has a library, but there's no measured boot support. There's poor documentation, and it's really adapted to Google and Chrome OS. It has been developed for Chrome OS, and there are multiple slots in the firmware in the flash. There's something like a failure system, and you can there's one read-only copy, and so there's this AB or ABC update scheme. It's really done very well. And in the end, it's really just a library which has protection mechanisms, and the protection mechanisms are based on the flash. So you don't expect you to use SOC mechanisms, but you will really want to have the SPI protection directly. There's an SPI no flash protection, so the chip has its own protection mechanisms. It's based on cryptographic keys, so really normal keys, no certificates. So, well, and the last part now is about an old idea for a new approach. So Linux boot, I didn't mention that. Most of you have probably heard about that. It was in the news. It's very well liked. And what it's about is that Linux boot in this project, it was a Google project. It's under the GPL v2 and BSD licenses. And the idea is that the parts of the firmware are being replaced by the Linux kernel. So the driver layer that you can replace that with a Linux kernel because it already has drivers. The kernel really is only drivers. So many drivers as the Linux drivers. No other kernel has that. So you can replace the driver layer completely, and you can more easily find developers. Linux developers are easy to find. Firmware developers are far away and few and far between. and there are very few code duplication. There are well-tested drivers, which means they have been very well tested, well tested, but better than those in the firmware. And you can also replace the bootloader. So you really don't need the system bootloader. You can replace the firmware bootloader. So here's what it looks like. You have a pre-RAM. You just cross out the driver layer and replace it by the Linux kernel, and strike out the bootloader and replace it by Linux user space. So how does that work? Everybody knows the Linux kernel. So you know initram fs, that's the Linux user space, and Linux kernel is the Linux kernel. And you take a complete Linux kernel, you put an initram fs, and it'll just run. Sounds easy, is not quite as easy, but if you really look at it, at the top there's a firmware, core boot, U-boot, Tiono core, host boot, and there's the Linux kernel stuff there, and it works, but there are some limitations. There are some to-dos that have to be done. One is the PSI device enumeration isn't yet activated. It's there, but it's not in there. The system management mode isn't there. Native graphic initialization already works. The Linux kernel already initializes the graphics, and it works, and you can do that in the firmware, including 3D acceleration. It's great. The only problem is really ACPI tables and E820 tables. It's a requirement for the kernel. They are not there. You have to think about that. We're not quite sure yet. And there's only one bootloader implementation, and unfortunately. So the initramfs is about the Linux kernel. We take the standard Linux kernel. Initramfs is uroot, and it uses Golang initramfs generator. It works like BusyBox, can add binaries, and you can use and it supports multi-boot v1, KXX support, and you can use any operating system, BSD, Windows, Linux, whatever. And there's a UEFI tooling, and there's a core board interface support. And system boot is the bootloader about which I've been talking. It's completely implemented in Golang. The first bootloader in Golang, I don't think there's any other. And all that is based on uroot and this BusyBox initID generator. And from the hard disk, you can use grub and grub2 or syslinux, or via network with DHCP. And you just do a KXX and boot into the operating system. There's a very wide and measured boot. Firmware variables only for core boot, not for UEFI. But if you're interested in that, look at that. It's just easy. It's all Golang, and it's quite nice. And you can maybe do graphics output or whatever. It's not too hard. Well, the conclusion is there's a lot of open source firmware hardware. The Open Compute project, that's a huge project. They have open source hardware with core boot. There's the Facebook Open Cellular. I've talked about that. There's Purism. They make laptops with core boot, Google Chromebooks. There's also all open source firmware. And PC Engines APU, it's around 90 euros, core boot. There's Scaleway, a hosting provider, has changed over to core boot to x80 on the x80 systems. Raptor Computing System, Talos, they have the Open PowerPC. They also don't have PCs, they also have servers. They are still quite expensive, but they are around 1,000 euros now for the main board. You can almost afford it. Then there's the Microsoft Surface, uses the open source firmware and lots of embedded boards. And if you want to do something with open firmware, just do it, right? All these already are supported by open source firmware. Then, I founded the Open Source Firmware Conference. It was there last year, and Google, Intel, Facebook, OpenSUSE, 150 attendees. It was in Erlangen in Germany, and Coreboot Linux Board was also there. And this year it will be in Silicon Valley. If you want to go there, and you are FOSS developers and students, and we can also get those people there. It's planned for the mid of September next year, and it'll be a bit bigger. And here's the last slide. Please visit our assembly. We have an assembly just like we did the previous years, 30 seats. You can have your hardware flashed if it is supported. We'll have workshops, or you can ask people who will help you. We have a demo setup to play around with. And we do that for core boot, Tiano core, U-boot, Linux boot, and system boot U-root. So just drop by and take a look.
bin froh, dass ich nicht mehr mit Toggle Switches booten muss.
I'm froh that I don't have to boot anymore with toggle switches. Are there any questions after this very interesting presentation? It was very interesting and very educational. Please come to the microphones. We have 1, 2, 3, 4, 5 different microphones. There's already one microphone. 5, 4.
Genau, vielleicht soll ich spezifizieren. Fragen.
A question is a sentence with the question marks afterwards.
Beinhaltet nicht deinen ganzen Lebenslauf.
So a question doesn't include your life story. How is this integrated with RISC-V? Do you have some plans for that?
So there are different ways. U-boot has support for RISC-V or RISC-V. Core boot has RISC-V support. And if you want to play around with that, you just get core boot, or maybe U-boot takes a bit longer. You can play around with it. They're just doing it with these two platforms. There's RISC-V support.
There's a question on microphone 1. I'm interested how this is integrated with the consumer products, for example, the ThinkPads you mentioned. So the new ones might have a problem with the interboot guard, so you cannot simply add core boot there. So how does it work with that?
So with newer laptops with core boot or something like that, the thing is the modern laptops have a feature by Intel which is called root guard, and Intel, Dell, Lenovo, and HP can protect the firmware with that from modifications by a secure boot mechanism from the South Bridge. So we can't get around that, but there are laptops where that has been switched off because the manufacturers say we want core boot installed. So you can buy from Purism, for example, and you can buy Chromebooks. They all have this, and there you have the possibility to do things like that.
So far we have no questions from the internet. Microphone number 3, please. The question to the workflow. When I use Linux boot as a firmware, when I'm booting with Linux boot, is the kernel that is working as a firmware, so that I'm using as the starting the machine? Is it the same that I'm actually running the operating system, or am I replacing it with a different kernel?
So with Linux boot, the kernel is being replaced by a new kernel. So the Linux boot kernel is only for hardware initialization because it should be small. So there's still restricted memory on the NOR flash, so it shouldn't be too big. And later it adds via kexec a new kernel, yes.
Gibt es weitere Fragen?
Are there further questions?
Nein?
No?
Sorry.
Excuse me.
Dann helft mir dabei, Philipp, für diesen genialen
Please thank Philip for this ingenious talk.
So there are now standing ovations here in the front, and thank you. Yes, thank you very much.